Okay, so we have seen this is a the finite difference approximation is very useful, but it is still an approximation, right? And we are very interested in, when we make that approximation, how much error we are committing ourselves to. That error is called the truncation error. So the truncation error is defined as, let me call it tau as the truncation error. Now the truncation error is the difference at the ith grid point, is the difference between the thing I have written down for many times, the finite difference approximation, minus the second order derivative we want to approximate at x equal to xi. Okay, how do we analyze that truncation error? Taylor series. Okay, Taylor series approximation. So basically, we do the same thing as we did yesterday, but a little bit differently. We want to expand the Taylor series to long enough such that we get the first term that is non-zero. Okay, so let's say I'm going to expand ui plus 1 equal to something, ui equal to something, and ui minus 1 equal to something. Actually, I will put minus 2i to ui. I'm going to, when I write down every term, I want to add them up to see if they are zero or not. Well, I'm going to write down the whole truncation error divided by delta x squared divided by delta x squared, and minus partial square u partial x square. Okay, I'm going to basically write down each term, and I'm going to look at where the first non-zero starts to occur. So for the first term, let me actually do the second term first, because it's easiest. I want to expand everything around ui. So this is just that, and all the other terms are zero. For the first one, I have 1 over delta u squared times ui, but there are more terms relating to first order derivative, second order derivative, etc. For the first order derivative, ui plus 1 is equal to delta x. The plus is delta x times the first derivative. So the delta x cancels with 1 of the delta x squared, becomes 1 over delta x. And I have partial u partial x at grid point I. Okay, and there are also second order terms, but let's leave it here for now, and I will expand other terms. So this one is also 1 over delta x squared times ui, but this is minus delta x times partial u partial x. And also the second derivative term, will leave it to 0 because we haven't seen second order derivative yet. All right. And here we can see that if you add them up together, this cancels. If you add them up together, this also cancels. All right. So these terms do not contribute to the truncation error. Now let's start the second order derivative. The second order derivative, I have a half of delta x squared, which exactly cancels with the delta x squared. We have partial square u partial x squared. And here we have the same thing. Now we write this down, minus partial square u partial x squared. They cancel. All right, so that's good. That means our approximation error, our truncation error goes higher and higher order. And now yet another term, it's going to be minus delta x over 6, 3 factorial, times partial cube u partial x cube. Oh, it's plus, and this one is minus. Again, they cancel. All right. And finally, we get to the term that doesn't cancel. Delta x squared over 4 factorial, which is 24. It's the fourth derivative of u with respect to x. And this, because it's an even term, I have both pluses. Ooh. 4. Ooh. Anyway. Okay. So now we know what the truncation error is. The truncation error, if I add them all together, everything cancels except for the last one. We want to expand the Taylor series to the first one that doesn't cancel, which in this case is delta x squared over 12 times the fourth order derivative of u. And of course, there are more terms, but they decay faster than that delta x squared. So I'm going to write delta x cubed. But this is the important term. This term determines when delta x is small enough. This term determines how fast the truncation error goes to 0 as delta x shrinks. So it depends on delta x. It also depends on the fourth order derivative of u. Question? So the question is, would the approximation error, would the truncation error be larger or smaller if we approximate different order of derivatives? The answer is not clear, because it depends on what scheme you use to approximate these derivatives. For the second order derivative, I would say we are lucky that we have a very compact scheme. A compact means it only involves 3 terms. That has pretty good approximation error. It's delta x. First of all, it goes delta x squared. Second, it's divided by 12, right? So I mean, this means the truncation error is very good. If you want the approximation error to be even smaller, you're going to see these 3 terms are not enough. You need to involve the neighbor of neighbors in order to have your truncation error go even smaller. Of course, that makes your scheme more complex. It makes the matrix, your matrix A, less sparse, right? And for other derivatives, you can also derive different approximation schemes. And different schemes will have different truncation errors. And there are also trade-offs between how complex the scheme is and how accurate the scheme is. And also, don't forget stability. Stability is another very important aspect of this, but we are going to talk about that later. So it's always going to be a trade-off between stability, accuracy, and the complexity of the scheme. All right. We see also a lot of high-order derivatives. In fluid dynamics, I think first and second order derivatives are most common. Like in structural dynamics, I think you see up to fourth order derivatives and things like that. I'm sure in other applications you may see even higher order derivatives. Okay, so this is the truncation error, and we are going to see for more oscillatory functions. So if I have a function like this compared to a function like this, which one do you think have a higher truncation error? Let me use a different color. If I use the same scheme to approximate the red function and green function, which one do you think has a higher truncation error? The red one? Red one. That's completely correct. Because the more oscillatory a function is, even for the same magnitude, the more oscillatory or the smaller the typical delta x is, the larger the higher the derivatives are. Okay, so the red function has a much larger in magnitude, fourth order derivative than the green one. And therefore, if you apply the same scheme with the same delta x, you are going to have a larger truncation error for the red function. Or if you want the same truncation error for both functions, what can you do? Yes, you need a smaller delta x for the red function than the green function. So if you have a smooth function, you need less grid points to resolve it, to have a small enough truncation error. If you have an oscillator function, you need more grid points to resolve it. All right. Any questions on this?